morning all, my name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about image compression models. So, how we are compressing the image, what are the techniques and what are the models are there to compressing the image, what is the need of the image compression, we will discuss today. Image compression is a process of applied to a graphics file to minimizing its size and the bits without degrading image quality below an acceptable threshold. By reducing the file size, more images can be stored in a given amount of disk or memory space. The most common compression methods are JPEG tends to blur the appearance of lines, especially to a low resolution. In contrast, lossless image compression technique retain the original quality but do not compress the image as efficiently. Example include TIFF, GIF and PNG. So, image compression models are what are the image methods are there. Suppose JPEG is one type of method. Okay, JPEG is a one format. So, depends on your format of the image, we have to use the method to compressing the image. So, image compression is a process applied to a graphics file to minimize its size in bits without degrading the image quality below an acceptable threshold. By reducing the file size, more images can be stored in a given amount of disk or memory space. So, the most common compression methods are JPEG, and these are tends to blur the appearance of lines, especially at low resolutions. In contrast, lossless image compression technique retain the original quality but do not compress the image as efficiently, include TIFF, GIF and PNG. So, these are the image formats. If I am taking the GIF, it is a video. PNG, TIFF is a video. JPEG is the image. So, which one is the image and which one is the audio and which one is the video? So, depends on your format of the image, it will be changed. There are two types of image file compression algorithms are there. Lossless image compression and lossy image compression. When we are going for the lossless compression algorithms to reduce the file size while preserving a perfect copy of the original decomposition image. So, lossless compression generally but do not always results in a larger file than lossy compression. So, lossy and lossless. Another one is a lossless compression. So, it is an algorithm to reduce the file size while preserving a perfect copy of the original uncompressed image. Lossless compression generally but do not always results in a larger files. But lossy compressions, both are very common in use. An example of lossless compression is a zip archive files, and examples of lossy compression is a JPEG file. Okay, so image compression are the two types. Lossy image compression, lossless image compression. If I am taking one example, what is a lossy image and what are the lossless? Suppose I am taking RAR file or JPEG file. So, image compressions are two types: lossy image compression, lossless image compression. Better example is lossy is a JPEG. When I am going for the lossless is a GIF file. Why? Because GIF file is a security is there, but lossy image is a JPEG. Why? Because maybe noise will occur. Need to use filters. So, image compression involves reducing the amount of data or bits required to represent a digital image. This is done by removing redundant information. Image compression is crucial for efficient storage, retrieval of the image transmission, and manipulation of the images. So more generally, data compression involves the efficient representation of data in digital format. So information theory, a field pioneered by Claude E. Shannon in the 1940, the theoretical basis for the most data compression techniques. So finally, we are discussing about the image compression. This image compression, we are reducing the amount of data or bits to be reduced. So reducing the amount of bits or data to be required to reduce this one to represent the digital image. This is done by removing redundant information. Image compression is crucial for efficient storage, retrieval, transmission, and manipulation of the images. More generally, data compression involves the efficient representation of data in digital format. So, information theory is an important role for the image compression or reducing the image data. That is the field pioneered by Shannon in 1940, the theoretical basis for most data compression techniques discussed. So, the compression can be either lossy or lossless. In lossy compression, one can achieve higher levels of data reduction with less than the perfect reproduction of the original image. So, compression can be either lossy or lossless. That is the information preserving. But in the lossy compression, one can achieve higher levels of data, reducing with less than the perfect reproduction of the original image. So the data compression refers to the process of reducing the amount of data required to represent a given quantity of information. So if I'm taking the data compression means image compression. The process of reducing the amount of data required. So number of bits should be reduced. Reduced to represent any given quality of the information. The various amounts of data may be used to represent or describe the same information. Some representations may be less efficient in the sense that they have data redundancy. So if I'm taking two number of information systems, that is N1 and N2, the carrying of the units or bits in two data sets that represent the same information, the relative redundancy RD of the first data set is defined as RD equal to 1 minus 1 by CR. 1 minus of 1 by CR. So here CR equal to N1 by N2 is called the compression ratio. So compression ratio CR compression ratio equal to N1 by N2. For images, data redundancy can be of three types: coding redundancy, interpixel redundancy, psychovisual redundancy. So in the coding redundancy, this refers to the binary code words used to represent gray values, and interpixel redundancy, this refers to the correlation between adjacent pixels of an image, and psychovisual redundancy means this refers to the unequal sensitivity of the human eye to different visual informations. Okay, three data redundancies can be there. Three techniques that are data redundancy: coding, interpixel, psychovisual. Okay, a fidelity criteria or error criteria is required to quantify the loss of information, if any, due to a compression scheme. Objective fidelity criteria is based on some quantitative function of the original input image and the compressed and the subsequent decompression of the image. So, if I'm taking the fidelity of the criteria or error criteria is required to quantify the loss of information, if any, due to a compression scheme. Objective fidelity criteria are based on some quantitative function of the original input image and the compressed and subsequently decomposed image. So, subsequent or subsequent or decomposition of the signal. That is the root mean square error, RMS error, which is defined as the square root mean of the MSE, RMS of MSE. So E of m comma n equal to f dash of m comma n minus f of m comma n. Here f of m comma is the original image, f dash m comma is the reconstructed image, E of m comma n is the error image. So original image f of m comma n, reconstructed f dash, and the error image is the E of m comma n. So E RMS equal to 1 by mn into summation m equal to 0 to m minus 1, n equal to 0 to n minus 1. That is f dash of m comma n minus f of m comma n whole square of 1 by 2. A related measure is the mean square signal to noise ratio, SNR. So here SNR RMS equal to summation m equal to 0 to m minus 1, n equal to 0 to n minus 1, f dash of m comma n half whole square by m equal to 0 to m minus 1, n equal to 0 to n minus 1, f dash of m comma n minus f of m comma n. So already we know that original image, f dash equal to reconstructed image. Reconstructed image. So f dash of m is a reconstructed minus original and reconstructed. So the RMS value of SNR denoted as SNR RMS is the square root of SNR RMS when the ultimate image is to be viewed by a human. Subjective fidelity criteria maybe are more appropriate. Here image quality is measured by subjective evaluations by a human observer. So ratings by the number of human observers based on typical decompressed images are averaged to obtain the subjective fidelity of the criteria. So the RMS value of the SNR is denoted as a SNR RMS is the square root of the SNR RMS when the ultimate image is to be viewed as a human. Subjective fidelity criteria maybe are more appropriate. The image quality is measured by the subjective evaluations by a human observer. The rating of the number of human observers based on typical decompression images are averaged to obtain this subjective fidelity criteria. So it is a general compression system of the model, that is the two types, encoder and a decoder. Here f of x comma y is the original image, output is a compressed image. So what are the stages from input to output? Input to output. What are the stages from original image to the compressed image? So input is a f of x comma y converting to the source encoder. What is the use of source encoder means? It removes the input redundancy. So after then it is going to the channel encoder. It is the first stage. Second stage, channel encoder. That means increasing the noise immunity. If there is any noises are there, our immunity will be increasing, or we are reducing the noise immunity or noise is there. And third stage is the channel, means transmitting encoded image. So transmitting the encoded image means we are applying the filters here. So source encoder, channel encoder. Here channel encoder, we are increasing the noise immunity, but noise is occurred. Transmitting the encoded image means filters are using to reduce the noise. And in the fourth stage, channel decoder, that means inverse operations of the source encoder. So what is the source encoder here? We are inverse operation. Okay. So inverse of this one is the channel decoder. And finally, fifth stage is a source decoder. Okay. Source encoder and source decoder. And finally, we are a compressed image. So input to output, nothing will happen. What is the means? Image compression is there without a noise. Okay. So it is the up to this one encoder. After the channel, it is the decoder. Okay. It is the decoder and it is the encoder. So channel is nothing but it is a mediator between the encoder and decoder. It is a general compression system of the image. And what are the compression techniques are there? So lossy and lossless. There are two. We are dividing as a two methods: lossy or lossless. When I'm going for the lossless, run length coding, Huffman coding, and Shannon-Fano, arithmetic, and dictionary based. So these are the 5 types of lossless and lossy images: lossy predictive and vector quantization, block transform, JPEG, and MPEG. These are the 5 types are there. So lossy image compression, lossless image compression. In the lossless, 5 types are there. In the lossy also, 5 types are there. So what are the 5 types means? Run length coding, Huffman coding, Shannon-Fano coding, arithmetic coding, dictionary based coding. And lossless means lossy predictive coding, vector quantization, and block transformation, JPEG, and MPEG. So these are the another transformation techniques for the lossless and lossy. So here one example of figure A, that is a lossless lossy. So lossless means I'm taking the original image, that is f of m comma n. So compressor means compression technique I'm going. So restricted is it is a output is there, that is a f dash of m comma n. Here lossy f of m comma n. So it is compression technique I'm taking f dash of m comma n. So what is the difference means here it is a lossless lossy. Okay, best example it is a JPEG. It is a RAR files or WIN files or whatever may be. Okay, so lossless and lossy are the two image compression techniques. In the lossy, 5 types are there. In the lossless, 5 types are there. So it is another example for the image compression model. It is a encoder and it is a decoder. Okay, figure A is the encoder and figure B is the decoder. At the encoder, f of x comma y is the original image. Source encoder, channel encoder, channel and channel decoder, source decoder. So source encoder means where entropy is there. Channel encoder means noise is reducing. In the channel means we are using filtering technique. Okay, channel decoder means channel encoder opposite to the channel decoder, source encoder and source decoder. It is a decoding, compressor, decompressor. Compressor at transmitter side, decompression at receiving side. So it is at completely input side. It is completely at output side. So image compression are dividing as a encoder and decoder. At the encoder side, 2 stages: source encoder, channel encoder. At the decoder side, 2 types are there: channel decoder, source decoder. Okay, input is I'm calling as f of x comma y, and the compressed image is a f dash of x comma y. At the input stage or encoder side, the output is a compressor. At the receiver side, it is a decompressor. And another block diagram of image compression model: f of x comma y is the input and original image. Here first stage is a mapper, quantizer and symbol encoder. It is a completely encoding, and at a compressed image, the image is compressed. At the output stage, at the decoder side, it is encoder, symbol encoder is there. Output side compressed image, symbol decoder. Here symbol encoder and symbol decoder, inverse mapper. Mapper is there now. It is the inverse mapper, and f dash of x comma y is the output image. It is a decoder. So f of x comma y is the original image. It is also output image with compression and decompressing, compressed image and decompressed image. So what are the stages means? At the encoder, mapper, quantizer and symbol encoder. At the decoding side, symbol encoder, inverse mapper, and output is a f dash of x comma y. It is a output image with compressing and decompressing. So original image, source encoder, channel encoder. It is an encoder. Channel decoder, source decoder. It is a f dash of m comma n. So f of m comma n and f dash of m comma n. Source encoder, channel encoder is the encoding system. The channel decoder, source decoder as a decoder is, and that is f dash of m comma n. So we are dividing as a encoder and decoder. Encoder plus decoder is the image compression. Image compression and decompression system. So it is provides to certain level of immunity from noise that is the inherent at any storage or transmission system. If the channel is not prone to noise, this block may be eliminated. The channel could be a communication link or a storage retrieval system. Channel decoder and source decoder invert the operations of the corresponding encoder blocks. And we will mainly concentrate on the source encoder or decoder blocks and not on the channel encoder and decoder steps. Okay. So in the image compression, two stages. This certain level of immunity from the noise that is inherent in any storage or transmission system. The channel is not prone to noise or the block may be eliminated. The channel could be a communication link or a storage retrieval system. The channel decoder and the source decoder invert the operations of the corresponding encoder blocks, and it will be mainly concentrate on the source encoder and the decoder blocks and not on the channel encoder and decoder steps. So in the 2D system of redundancy system, three types of redundancies in a 2D intensity arrays. Okay, it is a 2D. Why? Because two-dimensional. So coding redundancy, spatial and temporal redundancy, and so we are going for the coding redundancy. A coding is a system of symbols or letters, numeric, etc., used to represent a body of information. Each piece of information is assigned a sequence of code symbols called code word. So the number of symbols in each code word is the length of 8-bit. So length I am taking as a 8-bit. So this 8-bit, the code is a system of symbols or letters A to Z and numbers 1 to 9 or 0 to 9. So it is assigned a sequence of code symbols are called a code word. The number of symbols in each code word is length of 8-bit. So 0 to 7, that is a 8-bit. So spatial and temporal redundancy. Because of the pixels of the most 2D intensity arrays are correlated spatially. Example, each pixel are similar to dependent on the neighboring pixels. The information is unnecessarily replicated in the correlated pixels in a video sequence or temporally correlated pixels nearly frames also duplicate information. The irrelevant information or the 2D intensity arrays contain the information that is ignored by the human visual system. It is redundant in the sense that is not in the used. So there are three types of redundancy in the 2D intensity: coding redundancy, spatial and temporal redundancy. So if I am going for the coding redundancy, assuming that RK is a retrieval function 0 to L minus 1, it is used to represent the intensities of M into N image, and the each RK occurs with the K equal to 0 to L minus 1. So PR of RK equal to K equal to 0 to L minus 1, where L is the number of intensity values and NK is the most number of times that K equal to 15 intensity appears of the image. So the number of bits used to represent the each value of RK equal to I of RK, then the average number of bits required to represent each pixel equal to L average equal to summation of K equal to 0 to L minus 1 I of RK into PR of RK. So already we know that PR of RK and already we know that IR of RK. So This IR of RK number of represents each value of RK. And PR of RK is occurring with the probability. So another one is a spatial and a temporal redundancy. For an image constant intensity lines in the corresponding 2D intensity arrays, all 256 intensities are equally probable. So 0 to 255 intensity values are there. That means 256 values. All 256 intensities are equally probable. The pixels are independent is vertical direction. Since pixels along each line are identical, they are maximally correlated in the horizontal direction. When the image of constant intensity lines are represented as conventionally 8-bit intensity array, it cannot be compressed by variable length coding alone. Such image can be represented as a sequence of run length pairs where run length pair specified the start of the new intensities and the number of consecutive pixels that have that intensities. Okay, when I'm going for the 256 intensity values are equally probable. Pixels are independent or vertical defining. Since pixels are each line are identical, they are maximally of the horizontal. But the decomposition of the image, that array cannot be compressed by the variable length coding alone. Such image can be represented as a sequence of run length pairs, where run length pair specified the starting of the image with the new intensity and the number of consecutive pixels that have the intensities from 0 to 255. Total 256 intensity values are there. The basic compression models are Huffman coding, Golomb coding, arithmetic, algebraic coding, run length coding, one dimensional, two dimensional, and symbol based coding. So mostly we are taking Huffman coding, arithmetic coding, algebraic coding, run length coding, symbol based coding. Most probably are taking 4-5 types, but basically the image compressions are 8 types. Huffman coding, Golomb coding, arithmetic, algebraic coding, run length coding, one dimensional, two dimensional, symbol based coding. So these are the image compression models. So in the image compression model, the impression process is applied to a graphics file to minimize its size and the bits without degrading the image quality of the acceptable thresholding. So not changing. So the most common compressed methods are JPEG and to blurring the imprint. When I'm going to the blurring of the image, these are calling as a noise. The image appearance of the lines, especially at low resolutions. In contrast, lossless image compression techniques retain the original quality but do not compress the image as efficiently. So TIFF, GIF, and PNG are the best examples of the images. So there are two types of images, that is a lossy and a lossless. So image compression, lossy image compression, lossless image compression. So JPEG or zip files are the lossless, and when I'm going for the JPEG is a lossy impression. So noise will be occurred. Need not to use the filters to reducing the noises. So the image compression involves reducing the amount of data or bits required to represent a digital image. This is done by removing the redundant information. Image compression is crucially efficient storage, retrieval, transmission, and manipulation of the images. So more generally, data compression involves the efficient retransmission of the data in digital format. So the image theory or information theory is the pioneer of Shannon Fano in 1940, the theoretical basis of the most data compression techniques. The compression can be either lossy or lossless. But if I am going for the lossy impression, the data will not be lost. Only the pixels of the higher order values will be changing. And the data compression refers to the process of reducing the amount of data required to represent a given quantity of the information. The various amounts of data may be used to represent or describe the same information. Some representations may be lossy or less efficient in the sense of they have to the data redundancy. So the data redundancy R equal to 1 by 1 minus of 1 by CR. CR equal to N by N2. So CR is nothing but a compression ratio. But here three types of data redundancies are there: coding redundancy, interpixel redundancy, psychovisual redundancy. In the coding redundancy, this is refers to the binary code words used to represent gray values. Interpixel redundancy, this refers to the correlation between adjacent pixel of an image. Psychovisual redundancy, this refers to the unequal sensitivity of the human eye to the different visualization information. So, a fidelity criteria or error criteria is required to quantify the lossy or information of any compressed scheme. Objective fidelity criteria is based on some quantitative function of the original input image, and the compressed is subsequently decompressed image. So, the root mean square error, which is defined as the MSE, square root of MSE. So, E of M comma N is equal to error equal to reconstructed image minus original image. It is a error IARE is equal to 1 by mn, m equal to 0 to m minus 1, n equal to 0 to n minus 1, f dash of m comma n minus f of m comma n whole square whole power 1 by 2. It is the related measurement of root mean square with signal to noise ratio SNR, and the RMS value of SNR denoted as a SNR RMS. So, the ultimate image is to be viewed as a human. Subjective fidelity criteria may be more appropriate. The image quality is measured by the subjective evaluation of the human observer. Rating of a number of human observers based on typical decomposition images are averaged to obtain this subjective fidelity criteria. So, it is a block diagram of image compression model. F of x comma y is the original image. F dash of x comma y is the compressed or decompressed image. We are dividing as a encoder and a decoder. At the source encoder, it is the first stage of the image. It removes the input redundancy. At the second stage, that is a channel encoder to increasing the noise immunity to reducing the noises. At the third stage of that is a channel that transmitting the encoding image. We are using filters here to reducing the noises. And the fourth stage means it is a decoder. It is the first stage of decoder, that is a channel decoder, and a source decoder f dash of x comma y. So encoder and decoder, two different stages are there for compression and decompressing. So lossless image compressions are 5 models or 5 types: run length coding, Huffman coding, Shannon-Fano coding, arithmetic coding, dictionary based coding. And the loss image is a lossy protective, vector of quantization, block transform, JPEG and MPEG. So lossless is the original image with the compressed, that is a restoration. Loss is the original, compressed, it is a restored. Okay. So encoder and decoder. At the encoder side, we are calling as a compressor. Decoder side is calling as a decompressor. Okay. F dash of x comma y original. F dash of x comma y is the compressed. Or compressed or decompressed image. So source encoder, channel encoder or the encoder. At the decoding system, channel decoder and source decoder. So another example of image compression models are encoder and decoder. At the encoder state, mapper, quantizer, symbol encoder. At the decoding side, symbol decoder, inverse mapper. So f dash x comma is the encoding or decoding or compressed or decompressed image. So that is a f dash of x comma y. So f of m comma n is an input and f dash of m comma n is an output. So what is the stages are there means source encoder, channel encoder, channel decoder, source decoder. Okay, encoding is for compressing. Decompressing system. Okay, and it provides the certain level of immunity from noise that is inherent in any storage or transmission of the system. If the channel is not prone to noise, this block may be eliminated. If the channel could be a communication link or storage retrieval system, the channel decoder or source decoder invert the operations of the corresponding encoding blocks. Okay, at the output stage only we are using the concentrating of the source encoder decoder blocks are not on the channel encoder or decoder steps. So three types of redundancies are there: coding redundancy, spatial and temporal redundancy. And the coding redundancy, what is the formula means? We are taking the PR of RK, L average equal to summation k equal to 0 to L minus 1 RK into PR of RK, and it is a code redundancy. And spatial temporal is a image constant intensity lines with a 2D intensity array. The 256 intensities are equally probable. The pixels are independent in vertical direction. Since pixels are along with each line of identical, they are maximal correlated of the horizontal. And the direction when the image of constant intensity lines are represented as convention of 8-bit intensity array, it cannot be compressed by variable length coding alone. Such images can be represented as a sequence of run length pair, where run length pair is specified at the start of a new intensity of the number of consecutive pixels, that is from 0 to 255. That is a 256 intensity levels are there. What are the major basic compression methods are means? Huffman coding, global coding, arithmetic coding, LZW coding, run length coding, one-dimensional compression, two-dimensional compression, and symbol-based coding. These are the compression methods. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.